Welcome to another video for organic chemistry. In this video, we're going to be discussing resonance structures. So this occurs when more than one valid Lewis structure can be written. Okay, so for example, nitrate, NO3 with a negative charge. If I can draw out the molecule and what it looks like. So here I have Lewis dot structures signifying, showing all the valence electrons each element has. Okay, and here I have the bonds. I'll make another video later showing how I created this and how that negative charge, that extra electron I throw into this molecule stabilizes the molecule into what you see here. So nitrogen needs at least one double bond. And you'll notice that I have 3 oxygens surrounding it. Okay. Now notice that double bond. Okay, that double bond can actually switch over from the top oxygen to the bottom oxygen, the bottom right. Okay, so that double bond switches positions. Now the atoms don't switch positions, they remain the same. Okay, just notice how that double bond can go from one element, one bond to another. So one structure, like the one that you see right now, it's actually inadequate. This is an inadequate bond structure. It's not accurate as to what the molecule actually looks like. In reality, all 3 structures exist at the same time. So you'll notice here how I have all 3, and I have double pointed arrows indicating that it resonates from one molecule to the other. Okay, and I can have 3. So there's 3 different ways that I can draw this this polyatomic ion, and each of these is accurate, and at the same time each of these is not accurate. It's not adequate enough even to have these 3. Okay, and I'll show you why it's not adequate. So resonance or a hybrid is not flipping back and forth between resonance structures. This is why. Because you're not actually either one of these molecules, as you see, don't exist. They actually exist as one. So you don't have 3 molecules where that double bond is switching back and forth. Okay, so to be more accurate, you want to meld them together into one image, like you see here. Okay, also notice that I have my brackets. Okay, so resonance structures, I surround them with a bracket, and then you'll notice my negative charge on the outside. Okay, so like I said, I'll make another video illustrating better what this charge means and what that means for the electrons in that molecule. So this is the most accurate way to draw this molecule, where you'll notice I have a sigma bond that connects each of the nitrogen to each of the oxygen, and then I have a dotted line showing that that double bond that I was switching from one bond to the other, one oxygen to the other, actually exists at the same time with each of these elements. In fact, if you were to measure out the length of the bond or the length of the distance between nitrogen and any one of those oxygens, you'd find that it's not actually, you're going to find that not one oxygen is a double bond length or a single bond. They're actually in the middle. So it's more like a bond and a half, if you will, for each one of those. So it's an average between a single bond and a double bond. Okay? So that's why the previous images were not adequate enough, because with some of the images you could see 2 of the oxygens had single bonds and one of them had double, and then that double kept switching. In actuality, it's more of an average between the double and the single bond to each of the oxygen atoms. So this is the most accurate way to draw it out, and then you'll notice that the lone pairs on each oxygen are shown there as well. Okay. So one way to look at this is think of a peach and a plum. When you genetically meld these together, you end up with a nectarine. You don't end up with a peach at 1 minute and then a plum in the next. You end up with one nectarine. It doesn't resonate back and forth. So it wouldn't be accurate to say it's more peach or it's more plum. It'd be accurate to say that it's just a nectarine. It remains a nectarine at all times. It doesn't go back and forth. Okay? And that's the same thing with resonance. Resonance, we're not going back and forth. Those double bonds and single bonds don't switch places. They remain or they create an average bond length between the elements in question. Okay, so it remains a nectarine at all times. So resonance, you have one molecule that remains at one time. All right, let's take a look at another example, and this is what's called a benzene ring. You'll notice I have 6 carbons, and you have alternating double bonds between each carbon. Okay, this is a benzene ring. Okay, you'll notice benzene rings, these are found in partially burned petrol fuels. Okay, they're also sweet smelling molecules for flowers. So this benzene ring, you'll notice again that double bond can switch places. Okay, in fact, it does switch places. So these double bonds continue to rotate. And with this one, I'll make another video showing the mechanism of what's actually happening and why these double bonds keep switching places. But for now, just understand the fact that these double bonds, these pi bonds, actually rotate around this benzene ring. Okay, so you'll notice that it switches now. Let me go back. Okay, look at that double bond switch. Okay, so they jump places. There you go. So again, a resonance structure, it's actually not accurate to just show one of these structures. I'm sorry, let me go, it's going ahead of me here. Okay, so this structure is not adequate, neither is this one, because that pi bond is circulating and it's switching around so often that you don't have a single bond or a double bond at any given moment. You have an average of a single and a double bond. And with the benzene ring, the best way to illustrate that is a circle inside of the benzene ring. Okay, so this is called delocalization, and this is the delocalization of either the positive charge or a negative charge that stabilizes the molecule. Okay, so that pi bond is destabilized. Those electrons that make up that pi bond actually rotate around the entire ring, and that's what creates the stability within the ring. The fact that those pi bonds, the fact that those delocalized electrons or the delocalized electric charge actually is shared evenly, it's distributed evenly throughout all the carbon molecules, and that creates a strong bond for the benzene ring. Okay, so this is the skeleton ring and how it would be signified. All right, so let's take a look at another classic example, ozone or O3. So if you look at this molecule, you'll notice the double bond on the left side. Okay, so here you have 3 oxygen atoms and all the valence electrons shown. Okay, now the goal for each element when you're bonding to another element is to find a full valence shell. You want 8 valence electrons showing. So if I look at this particular oxygen molecule, you'll notice that it has 2 lone pairs, which account for 4 electrons, and then a double bond, which accounts for the other 4 electrons. Each of those lines representing a bond. Those are bond lines representing 2 electrons. So I have 2 of them, so that means I have 4 electrons. In total, I have 8 valence or 8 electrons. So the oxygen element on the left has its full valence shell, so it's satisfied, it's stabilized. And you'll notice the oxygen in the middle has 3 bonds. It has 2 on the left and 1 on the right, which accounts for 6 electrons. And then the last 2 are that lone pair. So that's 8 electrons. Now, because of the way this is structured, there's a positive charge that is created on that middle element. And if I notice on the third oxygen, I have 3 lone pairs and 1 bond. Okay. Now, that particular structure creates a negative charge. So that negative charge offsets the positive charge. Now, for this particular molecule, that negative charge is actually a delocalized charge, which means that it is shared within the entire element, or within the entire molecule, that is. So that double bond will switch places. Okay, it'll switch and then causing the negative charge to switch over to the other side. And it just continues to do this back and forth. In fact, it does it so much, just like our previous molecules, that it is more accurate to depict this as having a shared double and single bond all at the same time. So it has, the bond length is neither single nor double, it is more of an in-between 1.5. And that negative charge, those negative electrons, are delocalized and shared throughout the entire molecule. And it just goes back and forth like this. Okay, so that does it for our discussion on resonance structures. Thanks for listening and good luck on your studying.